Here are some examples of problems about concavity and convexity. Problem 1. Determine the intervals on which f of x equals x plus 1 over x is concave and convex, and identify inflection points. To identify concavity and convexity of this function, we need to figure out what its second derivative looks like. The first derivative of x is f prime of x equals 1 plus minus 1 divided by x squared, or simply 1 minus 1 over x squared. The second derivative of f double prime of x, is equal to 1 over x cubed times 2, which is equal to 2 over x cubed. Now the function is convex when the second derivative is greater than 0, so 0 is less than 2 over x cubed. If we divide both sides by 2, this is 0 is less than 1 over x cubed, and if we take the reciprocal of a positive number, it's still positive, so this is equivalent to 0 less than x cubed. We also know that the cube of a number is positive if and only if the number itself is, so 0 is less than x. Now for where the function is concave, we have 0 is greater than 2 over x cubed. We can follow the same procedure to say 0 is greater than 1 over x cubed, and then 0 is greater than x cubed, or 0 is greater than x. So this tells us that the function f is concave all the way up until x equals 0, and then it becomes convex from x equals 0 on to infinity. Now the only possible point of inflection is where it changes between being concave and convex at x equals 0. However, this function's derivative, or second derivative, is not defined at x equals 0. In fact, the function itself isn't defined at x equals 0, so this can't be an inflection point. Problem 2. Find all critical points of f of x equals x squared minus 1 over x, and use the second derivative to identify the local extrema. To solve this problem, we're going to need to calculate both the first and the second derivative of f. The first derivative is f prime of x is equal to 2x, the derivative of x squared minus 1, times x minus the quantity x squared minus 1 times the derivative of x, which is 1, over x squared. And this is equal to 2x squared minus x squared plus 1. And all of this is divided by x squared. And this is equal to x squared plus 1 over x squared. And then the second derivative of f double prime of x, is equal to 2x times x squared minus x squared plus 1 times 2x. And then this divided by x squared squared, which is x to the fourth. Now if we factor out this 2x, then we're left with x squared minus x squared plus 1, which is just minus 1. So we have 2x times minus 1 divided by x to the fourth, which is equal to minus 2 over x to the third. Now let's use these to find the critical points in extrema. So the critical points occur when x squared plus 1 over x squared either equals 0 or doesn't exist. When this doesn't exist, x equals 0, which means that f of x is not defined either, so that can't be a critical point of f since it's not even in the domain, so we don't need to worry about that. But when it's 0, we have the numerator x squared plus 1 equals 0. So this means that x squared is equal to minus 1, but that can't be the case unless x is an imaginary number. This means there are actually no critical points. So it turns out we didn't even need to use the second derivative to figure out whether the extrema were minima or maxima.